Okay. This is 1.6 polygons. It's important to define what exactly a polygon is, and a few things to remember. But first of all, what is a polygon? A polygon, it's going to be a closed figure in a plane, which means it's going to be on a two-dimensional surface. It's formed by connecting at least 3 line segments. You can't have anything less than that. Triangle is the smallest polygon that you can have. Endpoint to endpoint, with each segment intersecting exactly 2 others. These 2 points are key when defining a polygon or seeing if a figure is a polygon. We're going to call each line segment, that's going to be called a side. Each endpoint where the sides meet is going to be called a vertex. So this is very similar in how you did angles. In the figure below, we have a 5-sided figure here, a 5-sided polygon. And there's another important property called a diagonal. And a diagonal is basically a segment connecting 2 non-consecutive vertices. This vertex and this vertex, they're not consecutive. They're not right next to each other. So we take a diagonal or a line to connect those 2 non-consecutive vertices, and we can do it throughout the figure and get all of our diagonals. Now this particular one has a interesting shape. Sometimes they have interesting shapes, which is kind of cool. So the different types of polygons that we're going to be talking about, we have convex versus concave. A polygon in which no segment connecting 2 vertices is outside the polygon. In a convex polygon, consecutive vertices share a common side, consecutive sides share a common vertex, and consecutive angles share a common side. Concave polygons is a polygon in which at least one segment connecting 2 vertices is outside the polygon. Visually, this is a lot easier to actually see. So here are your examples of convex polygons versus concave polygons. The thing I tell people is that notice in the convex polygons, each one of the vertices points outwards, points outwards, points outwards. And in the concave, it's caving in on itself. So it points inwards, or you have something that points inwards, points inwards. That would make these concave. A lot of people have trouble with the wording and remembering the wording. The thing that I tell people is if it points outward, all the vertices point outward, it's convex. All the vertices or a couple of the vertices point inward, it's concave. In identifying polygons, you have to tell whether the figure is a polygon and whether it's convex or concave. The first one, because of this point right here, we have 3 line segments that come to the same point. Remember, in the definition of a polygon, you can only have 2. So we have this line here, and this line here. They all come to the same point, which is right here. Since that is, you have 3 line segments intersecting, that means that it is not a polygon. So this would be no. This guy here, letter B, we have line segments that intersect. One here, and one here, so on and so forth. They only intersect in 2 points, so that's what makes this an actual polygon, and they are line segments. This is a convex polygon, again, because all the vertices point outwards. For C, this curve right here is not a line segment, so that makes this a non-polygon. So for D, this actually, again, is a polygon. You have all the line segments, and this actually is a concave because you have this guy pointing inwards. So this is not convex, it's concave. The number of sides of a polygon actually classifies it and tells what type of a polygon it is. The smallest one you can have is a triangle. And the next one up is a quadrilateral, quad meaning 4. Pentagon meaning 5. Hexagon meaning 6. Hexa. Hepta meaning 7. Octagon, octa meaning 8. Nonagon, decagon, and dodecagon. In the past, what I've seen people kind of have trouble with is the heptagon and hexagon because they sound very similar. these are just one of those things that you have to memorize and make sure you can decipher between the two. Hexa meaning 6, hepta meaning 7. Another property or properties of polygons that polygons can have are twofold. You have all sides are congruent in an equilateral. Equa meaning equal, lateral meaning side. All angles are going to be congruent in an equiangular. Equa meaning equal, angular meaning angles, so equal angles. If both of these properties are true, that means you're going to have a regular polygon. And it's going to be a convex polygon. So in example 2, classifying the polygons, example A looks at the notation. We see that all of the sides have a double dash mark in terms of the labeling, this double dash mark. So that automatically means that we're equilateral. Looking at the angles, they have the same arc marks in terms of the labeling, so that means automatically it's equiangular. And again, if it's equilateral and equiangular, we call it a regular. Since this has 6 sides, we call it a hexagon. For the next one, you have 4 sides. You count the 4 sides, 1, 2, 3, 4. So that means it's a quadrilateral. But none of the sides, not all the sides are equal, because we have a 2 dash mark here and a 3 dash mark here in terms of labeling. And again, for the angles, we have a 2 arc mark and a 1 arc mark. If the arc marks are different, that means automatically it's not equiangular. So this one would be a quadrilateral, and there's nothing really special about it. Well, you'll see in later chapters there actually is. For this one, counting the sides, again, you can count 1, 2, so on and so forth, and you have 12 sides to this figure. The angles are the tricky one. The sides, you can actually see all of them have a single dash mark, so automatically this is equilateral. But looking at it at first glance, you're like, oh yeah, this is equiangular as well. Well, if I look at this angle here is actually different than the right angle that I see here. So this is not equiangular. So all it is a 12-sided figure called a dodecagon, and it's only equilateral. Couple of applications with this, and again, you read the directions with this and you'll be okay. We have a table is shaped like a regular hexagon. If it's regular, it tells us it's regular. That means all the lengths of the hexagon sides are congruent or equal. It's asking us to find the length of the sides. All we do is set them equal to each other. When we set them equal to each other, we solve for x. X is equal to 8, and then we have 30 inches when we actually substitute it in. So, for the next figure, you have, again, a regular pentagon. It's regular, so that means all the side lengths are the same. We set them equal to each other. Now, this can be a little intimidating because you see the x squareds and the x squareds here. The great thing is that those x squareds, when you set them equal to each other, they cancel out. And you just solve for x. That's what we're asked to do. So x is equal to 2. And that's it.